Hi, we're team number 5, and we're going to present the methanol production process simulated in Aspen Plus. According to the National Institute of Health, methanol is considered as one of the most useful chemical products and is a promising building block for obtaining more complex chemical compounds, such as acetic acid. Its primary uses could be as a fuel, since methanol can be used in internal combustion engines. It could be also used as a solvent, since methanol is a solvent in the manufacture of resins, dyes, and adhesives, etc. It could also be used as pesticides, fungicides, and for antifreeze products, since methanol is a component of antifreeze and windshield washer fluid due to its ability to lower the freezing point of water. It's important to recall that learning this commonly used process of production is really useful for us as chemical engineers, since throughout the years the price for methanol has been increasing, converting it into one of the most useful components in chemical processes. This process is divided in three different sections. The first one consists under a formation of natural gas. For this, we use Penn Robinson as the chosen method since the majority of the components in this process are hydrocarbons. First, natural gas enters a heater where its temperature significantly increases in order to later mix it with vaporized water at an also really high temperature. Once mixed, the resulting fluid enters the bulb, where its pressure decreases to later enter a R-stoic type of reactor where the shown reactions are the ones taking place. For this, we chose the R-stoic type of reactor because the stoichiometry numbers were known. And these were the results for the first section on the process for methanol production.
In this part of the process, we have a few components. One of those are the heat exchangers, the E2 and E3. The purpose of this heat exchanger is to get more hot the streams for more efficiency in the process. For example, we take the exchanger number two. We need a hot stream, so the separator have a more efficient process and ha- separate more the heavy components in the stream, such as water. We also have a compressor with the purpose of, well, getting more pressure in the system. Uh, this part is essential. Maybe in Aspen we don't have a better good view of this, but the process can be really big, and we need a good pressure in the system. So that's why the compressor. And also, it's a compressor and not a pump, because a compressor works essentially with vapors, and we are working with vapor in this case. Well, we also have a mixer, so we can mix our stream, our inlet stream. In this case, is the stream number 9, and the recirculation stream, the R stream. The reactor is an equilibrium reactor. Um, we use this reactor because we have the equilibrium coefficients. That's why we use this type of reactor. We can also use this type of reactor when we know the kinetics with the kinetics factors. In this case, we don't, but we know the equilibrium reactor. Uh, my partner Uwe is going to explain the rest of the process.
In the outlet stream from the CAS-ECTR reactor, stream number 11 enters flash 2, where the goal is to separate methanol from the other compounds. Additionally, the temperature is lowered to 30 degrees and the pressure is increased to 83.4 bar. The upper stream is sent to splitter, which will recirculate material that has not completely reacted, and a purge where part of the unnecessary components is removed, taking some of the useful ones as well. The bottom stream from flash 2 passes through a valve that reduces the pressure to 2.6 bar before entering flash 3, which raises the temperature to 74 degrees to remove a big percent of methane. The bottom stream from the flash tree then enters the RAFRAC, which is used to further purify the compound by removing methane, ethane, propane, water, and hydrogen, finally achieving a methanol purify of 97%.
Thank you very much for paying attention in this presentation. In conclusion, uh, I'd say that the heat exchanger in this process is I believe, the most important. Is because our system is working with flash separators, with reactors, with branch racks, and in order to use this more efficient, I believe we need a hot stream. Why? An example is the flashpoint. As I say in few slides ago, getting a mix stream hotter is going to facilitate the separator from doing its work. Also, we have two reactors, and with hot streams, it work more efficiently.